Hi, everybody. Welcome to our meetup. This is our first test of the virtual environment, so hopefully it works out for everyone. Just a couple of housekeeping things. We have the text open. Once I hand off to Jack, I'll start monitoring, and just feel free to ask any questions you want. We're going to try and keep this as open and interactive as possible. And in terms of next month, we have a joint meetup that we are scheduled with Aaron Reinhardt and the Chaos crew. They were scheduled to have an event in person, but given everything that's going on, I know that they are looking into virtual options. So please keep lookout for that. That will be on April 21st, so we have plenty of time to figure out the logistics of that. But it's going to be a really exciting conference. There's some really good talks lined up. And it looks like we are going to try and get started in a minute with Jack Mannino. Is everybody? Let me check on the chat window. All right. It looks like Jack is in. So if you all are ready, I'm going to hand it off to him, and he will be presenting on WebAssembly.
So good evening, everybody. Would have been great to hang out with everybody, but kudos to the chapter leadership for making it a remote event and keeping us all from getting each other sick. So tonight we'll talk about WebAssembly. WebAssembly's pretty well supported across most of the browsers at this point. It allows you to run native code within the browser as well as standalone at near native speeds. And it allows you to essentially take your code and compile it, whether you're coming from Go, C, C++, or Rust, to a common compilation target and stack-based virtual machine that you can run in different places. So tonight we'll talk a little bit about WebAssembly and what it is as a specification. We'll look at how it actually works from a format perspective and how it's actually loaded into the browser. We'll look at some common security issues. Some of these things are memory corruption types of issues that we've dealt with in a lot of different places. And what we find is that the memory security model of WebAssembly partially mitigates against some of these, but we still have the ability to overwrite arbitrary memory. But it is a little bit different of a memory model if you're used to traditional register-based machines. And we'll talk through a couple different mitigations and things we can do to secure our WebAssembly code. As myself, I'm Jack Mannino. A lot of you know me. I used to run the chapter. Used to make it out there a lot more often. And then 2 kids and running a company later, I unfortunately don't make it out as much anymore. We are hiring. If anybody's local and in the job market for application security, let's keep in touch and maybe talk after this. Nowadays, I do most of my development in Go, Scala, and C++ for the most part. I've dabbled with Rust a bit. I just haven't taken up Rust as much of a hobby as I wish I would. I'm a New York Mets fan. Definitely disappointed that the baseball season is going to be delayed here, but it's for the best, right? So WebAssembly, often shortened to Wasm. And what it essentially provides is a bytecode format that we can run in different virtual machines. And it's a common format that we can, so think of assembly in a common format that everything essentially can be built in, right? It's similar. We, for the most part, for a lot of the major compilers, have the ability to target compilation for WebAssembly. WebAssembly is also supported in LLVM as well. So you can work with WebAssembly through LLVM toolchain as well. And what you get out of WebAssembly is, one, the most common use cases we see it used within the browser. So you can run really heavy graphics applications, things that we've done traditionally through plugins, extensions. We can run really sophisticated applications in the browser. We'll look into how it kind of gets sandboxed. So WebAssembly does give you some sandboxing and protection from the rest of the system. You can also run standalone WebAssembly applications as well, and plugins and extensions for different tools. And you're starting to see now WebAssembly is becoming a really popular format. So things like Envoy, which is used in service meshes for containers. Traditionally, you've had to write your plugins in C++, and now you can actually target WebAssembly as well. So they're actually using V8's, Chrome's V8, their runtime to do WebAssembly stuff. So pretty neat. And if you want to run WebAssembly, this is essentially how you can start that. So there's a JavaScript API and some common calls. And this is basically what you need to do to get a WebAssembly running in your browser. So you can fetch it, instantiate streaming, and we'll look at exports. But exports are any of the exported things within the module, and those are the things that are actually invocable via JavaScript. So you can talk to the WebAssembly through JavaScript, and this all obeys the same origin policy as well. So if you're running in the browser, you do have the same origin policy. You have some sandboxing within the browser, and a little bit more separation from the system, as opposed to if you're running WebAssembly on the box itself. And WebAssembly is pretty well supported through the major browsers at this point, so it's really not an issue of support at this point. And let's just take a look for really quick at pulling down a WebAssembly. Let's see here. All right. So if we go online, we can see there's lots of WebAssembly examples here. And we'll just pull one open, first one. And we'll open up developer tools. Where'd it go? There it is. And if we take a look at our network objects, we'll just hit refresh so it pulls them down. So we'll see here we have a Wasm file, right? And we can actually go ahead and download that. So I will open that in a new tab. That's going to then prompt me, let me run the WebAssembly. So now I actually have that WebAssembly file on my system here. All right, and I actually have this file here. So we can do a couple different things to get it back to a format we can work with. So for example, we can do Wasm to C on that Magnum file, and we'll do a more on it. And what we'll find is that it's really easy to get that back to a pretty easily reversible format. And let me just make that a little bit wider here. And we can do something similar as well if we want to do Wasm to what. So what is WebAssembly text? And we can get that back to WebAssembly format pretty quick, and we can dig through that. So getting code back from the WebAssembly to decompilation is pretty trivial. There's tools that do it pretty easily for you. So it's there's a bit that kind of gets messy. So there's optimization that happens and a few other steps. So sometimes things can be a little bit ugly to look at, but it's well within the realm of reverse engineerable. So that's just a quick example and kind of demo of the WebAssembly format. So it gets loaded into the browser. So think of like how we used to pull a Swift object out of the browser. And so if you want to grab that object, it's very similar. It's just downloaded and pulled into the browser. So with regards to a WebAssembly module, they're composed of essentially these sections. So the ones that are really important from a security testing perspective, the exports are things that we can invoke externally. Tables change things like function pointers around a little bit. So function pointers inside of WebAssembly work different than if we were working in a native file system with registers. So essentially, we end up getting tables to different things where we can have references to functions as opposed to getting direct memory access. So that is one thing that's a little bit different. There's a couple data types in the WebAssembly format. One of the things that gets interesting is when we look at stuff like control flow integrity and things that work on signature matching for functions and data types. What we find is that WebAssembly's limited amount of data types makes it more likely that we can overwrite or get around things like control flow integrity by clobbering other functions. With regard to control flow, so everything is essentially immutable. There's no dynamic code. There's nothing pulled in. So everything's known essentially at compile time there, including the control flow within the application. So these are an example of just the different control flow operators and opcodes here. So there's certain things you don't have, some jumps. You don't have like a direct go-to, for example. So if everyone remembers all the bugs we've seen because of go-tos, you don't have all that from a control flow perspective, but you can do, control call flow graphs from Wasm fairly easily. And so we looked at being able to basically go back and forth from the WebAssembly format back to more easily gleaned format. So it's really not super hard. So, web or obfuscation and things like that come into play here because, what we end up seeing is people push a lot more functionality into WebAssembly than they would just basically push into JavaScript. So you're more likely to have, more proprietary logic in there and things that you'd want to maybe keep away from an attacker. So WebAssembly's memory management model is interesting. So you have a linear memory model, and WebAssembly is essentially a stack-based virtual machine. So you push and pop things off of the stack, and things like heap and whatnot work a little bit differently. And inside of the WebAssembly, you also don't have the same access to directly call memory locations. However, you can still overwrite arbitrary memory through using unsafe memory functions. So you can still get a lot of classes of buffer overflows, format string bugs, integer overflows, etc. There's no inherent protections there, but it does give you a slightly different model that makes certain things like return-oriented programming and other techniques that people use to jump around and mess around with control flow. And additionally, if you're using some of the compiler protections around this stuff for control flow integrity, it makes it a little bit more difficult to attack those things at runtime as well. But those are things that you do need to build in when you compile your assemblies. And there's a whole bunch of different targets. So if you're using Golang, Rust, then your compilers do have support for pushing out WebAssembly. There's a bunch of different runtimes as well that are being used. V8's pretty popular, so V8 has first-class WebAssembly support. And depending on which parts of WebAssembly, so for example, if you're using WebAssembly system interface to do non-browser applications, then there's a whole swath of runtimes that you'd want to target at that point as well. So mscripting, and there's a handful of other compilers that are pretty popular. So they'll give you toolchain to compile your applications into things like LLVM and so forth. And here's the JavaScript API. So we looked before at instantiate streaming. That's the most common method of loading a WebAssembly. Over here on the right, we have different classes that we can call and invoke. from our applications as well. And what you notice is some of those correspond to the top level modules as well. So being able to reference function table, getting references, indices to those, so on and so forth. So a lot of WebAssembly is programmatically accessible through JavaScript. But the thing to note there is that you do have same origin protections and things like that. So when those are in place, then most of the browser protections work as expected. And getting into some of the security issues we can kind of run into. So memory corruption is always going to be a prevalent topic, especially when we're working with languages and runtimes that don't support garbage collection, and things like Rust and Go have made some really good strides with giving you memory protection against different classes of memory corruption bugs. And what you find is that some of those things are on and some of those things are off when you get into the WebAssembly mode. But some things, for example, like stack canaries and some of the common mitigations against some memory corruptions aren't actually necessary. And what we find is that those protections don't give us really anything in a WebAssembly. They're kind of NA. We can have injection, surprise. So we have interfaces between the WebAssembly and JavaScript. So we can communicate between the WebAssembly and the DOM in that way. So what we end up finding is that we do have some exposure for cross-site scripting. When we get into running WebAssembly outside of the browser and using WebAssembly's system interface, we want to be careful with regards to the capabilities that we assign to the binaries and the things we allow them to do. So you have a syscall-like interface that has so familiar with like Linux, POSIX, and everything like that. Very similar interface, but pared down a little bit more inside of the runtime. And as concurrency is increasingly added to WebAssembly, so in the initial WebAssembly MVP, there weren't the ability to do multi-threaded stuff, but that's become an increasing thing in WebAssembly as it matures. So let's take a look at everyone's favorite vulnerability of all times, cross-site scripting. So you can have cross-site scripting, especially when you have communications between the WebAssembly and being able to invoke JavaScript. So depending on the SDK you're using to build your WebAssembly code, you may very well have these different things that will let you invoke JS and interact with the browser application. So in an M scripting land, this is an example of anything arbitrarily run within here is going to run JavaScript. So you can pop up your pretty alert box here. You can run something a lot more malicious. This is going to be an example of something that's going to happen at the DOM for the most part. So this is going to be something you protect against in the WebAssembly. And then also, you may want to have defensive JavaScript as it consumes data that's coming back from the WebAssembly as well. We also have the classic buffer overflows here. So it's a little harder to do things like, especially if we have control flow integrity turned on, then techniques like return-oriented programming and using ROP gadgets and whatnot get a little bit harder to do based on the way function pointers and pointers work in WebAssembly. But at the same time, we can still overwrite variables in memory. So because we can overwrite parts of memory, we can still land back at the code we want. So some forms of buffer overflows do work. Things like integer overflows are going to work as well. There's no inherent protection in WebAssembly and the runtime that protects against these. But if it's things that do violate control flow and try to do control flow hijacking, then those are a little bit more tricky to pull off. So here's an example of classic format string bug. So you're allowed to use the %n, which allows you to write. So depending on the format string you control, there's different ways to kind of attack it. But you are able to overwrite, or I'm sorry, you can read memory in some of these scenarios. But if you try to write directly to linear memory and directly point at things, then you'll see JavaScript exceptions happen. So there's edge cases that allow you to overwrite things in some scenarios, but less. And importantly, you can essentially read memory locations that you shouldn't be able to. And in this example here, it's with that string in printf, obviously we're putting in a large amount of data that we control, and we want to wrap back around and be able to read the password out of memory. So WebAssembly in newer versions, there's an emerging specification for a full API. So it allows you to do a lot of things from the WebAssembly with regards to invoking files and system resources, working with sockets on the system. So similar to if you're familiar with how Linux works and capabilities and using them to gate various syscalls. So you have the ability to assign capabilities to the binary and what it's going to run with. And basically, when you assign those capabilities, that's going to dictate which syscalls. So they're not actually Linux and POSIX syscalls, but very, very similar. And it's clear when you read the standard that they borrowed a lot of ideas from other standards. At the same time, this is where it gets really interesting because you're going to have a much more robust interface to communicate with the WebAssembly application. So you can talk to other applications, can talk to the operating system, etc. So as you use these interfaces, it's definitely important to start thinking about what can you do outside of the WebAssembly. So things like using the WebAssembly as a malicious proxy, so on and so forth. Depending on what kind of powers in that WebAssembly will dictate, what an attacker is going to want to do. So it is important to limit the syscalls that are generally available, similar to how you do in Linux or running things in a container. You want to give an attacker the least amount of stuff that they can pivot to and use to further their attacks as possible. So use after free bugs also work in WebAssembly. So WebAssembly gives you a function pointer back to the function table, but you're still able to overwrite things in a use after free. So if anyone's basically what ends up happening in a use after free bug is first we've freed the memory, and now we're doing something else that points back to that at a later point in time. So now we have arbitrary memory that hasn't been deallocated that we can essentially abuse. So this is another class of vulnerability that you don't get any protections from WebAssembly either. With regards to mitigations, so let's talk about some of those. So WebAssembly gives you some additional protections for memory management, protecting control flow, but at the same time, you still need to code defensively, right? So it gives you a little bit of forgiveness. It gives you an extra sandbox, but it doesn't necessarily give you 100% protection from a lot of these vulnerabilities as we've seen. Control flow integrity. So this is one that you can turn on inside of your compiler there. And there's other flags that you can pass in as well. But essentially what happens with control flow integrity, because our code is immutable and the control flow of our application is known at runtime, then in theory there should be method signatures along the way that would essentially match what we expect the control flow to pass off to. So essentially that's built out, and if at runtime the application attempts to branch to something that's unexpected at runtime, then it'll raise an exception and disallow that behavior. So there is some performance hit for using control flow integrity, but given the protections that you get from it, it's really, really powerful stuff to use. Additionally, you do want to optimize your code and make sure you get rid of as many functions as possible that could potentially be called or exercised somehow. So essentially, as we went back and discussed before, there's 4 different types in WebAssembly. And the way some of the different protections work is that they look for signatures. So they'll look, for example, for a function that has a certain amount of parameters of a certain type. So if you have 1, 2 parameters and a combination of the common data types, it is possible to hijack control flow in some ways, as long as it's a matching method signature, a function signature at that point. So that is one scenario where if you want to reduce your surface a little bit, you do want to optimize your code and clean up all the stuff that shouldn't be getting put into compilation at the end. Cool. That's my initial crash course here to WebAssembly. So in conclusion, we looked at a couple different classes of memory corruption attacks, and we find that a lot of what's been a thing in the browser, or a thing in native code for years, is still there, but we have a maybe slightly narrowed attack surface. We want to use as much of the toolchain and protections as possible. And depending on the runtime, compilers, and different toys you're playing with, you do want to make sure that all of these things are available and also turned on as you build your applications. Cool. That's the end of it. I'm happy to take questions. Might have went a couple minutes quicker just because I have no one to actually look at.
Yes, can you hear me now? So thank you, Jack, for that presentation. I'm no longer on mute, so hopefully that's good. I hope you all can hear my lovely voice now. And there we go. So I just wanted to wrap up. If there are any questions, just throw them in the chat window. Yeah, so Jack, it does look like there is a question. So the question I'm seeing is, when you compile from memory safe language like Go or Rust into Wasm, do you lose those protections?
So at compilation, so there are, yeah, so some of those things work slightly different, but I mean, if your code, for example, so in Rust, right? So if you've prepared an array, right, and you're passing something in, so Rust will handle some of that stuff at compilation time. So you do get some of those. They'll at least help you from patterns, avoid passing in things that can violate bounds checks, but at the same time, not 100%. Yeah, so you do lose some of that, but not all of it.
Okay, cool. So yeah, we can hang out here for a few more minutes. I'll do some wrap up, and while we have Jack on the line, we can still just ask questions in the chat. Feel free to just throw something out there, or you can email him off the line too. Yes, a question just came in. Will this video remain on YouTube? Yes, we have our OWASP Nova channel, which has a couple of videos. And now that we are going through these virtual meetups, a lot more of them will be recorded. There have been some issues in the past with hooking up the camera and everything to get the in-person meetups recorded or distributed. But for these virtual meetups, it's very easy and very well integrated. So just to recap again, the next meetup is currently scheduled for April 21st. That is a joint effort with Aaron Reinhardt and the Chaos crew. That's going to be in Georgetown, but I know that they are, with everything going on, looking into virtual meetups. So hopefully we'll figure that out and get the information to you as we know more. So yeah, sorry, I see another Abdullah is asking about the recording. Yes, I can confirm that this is being recorded and that it will be within our channel. Once we stop the broadcast, it's automatically just going to be in the channel for view whenever at your convenience. So see here, without any further ado, I guess we can call it a night. And again, I just want to thank everybody for joining in our YouTube chat. I think we had 34 people in there talking and just saying hi. I know that this is a different format. It's going to take a little bit of getting used to, but in the effort of trying to be as health preventative as possible and trying to keep certain things contained. These virtual meetups are a great avenue to still get the information out there while staying and keeping everyone as safe as we can. So without any further ado, thank you everyone, and I hope you have a good and safe night. So take care.